Jessica, can you hear us, Jessica? Let's see if I message her. Okay, so through the previous homework 5, now I think you have a better understanding of the difference of these two. Which proof is proof by contraposition, and what proof is a proof by contradiction? Proof by contraposition. So we first formulate the contraposition of the theorem. Then we prove that contraposition. The contradiction is, we suppose the conclusion is false, we try to derive a contradiction. The contradiction may be contradict the first step, contradict the second step, contradict the last step, the contradiction with any one of the previous steps. The contraposition, we have a very precise statement. For the contraposition, we have a precise hypothesis, have a precise target. And for contradiction, we have the opposite of the conclusion, whether the contradiction arises during the proof. And we have a few more examples of this mathematical induction. So this mathematical induction is used to prove the statements that has infinite many cases. More. Sometimes I will just use induction for short. So it's about the propositions. Typically, we set a 0 or 1. And in our homework, we had a special case bigger than 7. Okay. Because propositions like this has infinite many cases. Have infinite many cases, we cannot verify them one by one. So what we do is this induction. We prove the one step, the next step, we prove this implication, then the base case implies all future cases. The examples we had last time. So for these two propositions, we proved it using the induction. Another one, slightly different. We consider the following proposition. Summation So here, this is the summation notation. It means we add many terms, but we don't want to write this every time, so we use the short notation. In this notation, M starting index, N the ending. We call this the common term. And the G is the summation index. Summation notation. When G equals M, the starting point we have the first term AM. The next term, so from M to N, goes to M plus 1, M plus 2, up to, until N, the ending term. So where we start at M, end at N, for AJ, each J, the summation. Okay, with this, let's write down the first few terms for this summation. Okay, Amy, what's the first term? Where would we start?
0.
So when J is 0, what is this number? A0.
Oh,
Yeah,
that,
do not simplify, just we just replace this J by 0. Amy, is this clear?
yeah.
So the first term, when we start at M, I will replace J by M. I got the first term. So here we start at 0. So I replace J by 0. I get the first term. Kira, what's the second term?
Plus 1 over 2 to the first?
Yes. So J runs from 0 to N, 0, 1, 2, 3, 4, up to N. The next term will be a few more terms, a few more people here. Aaron, next term.
Oh, that's 1 over 2 squared, I guess.
Okay. Jessica, can you hear us, Jessica? Okay, what's the next term?
Wait, could you repeat that?
Okay, so we had the first 3 terms. What's the next term for this summation?
1 over 2 to the third.
That's nice, yes. Okay, so it will be okay. Fred, can you hear us, Fred? Okay, maybe he will respond later. So this will be the last term is where we finish at n. So I replace j by n, j by n. Okay, now some special cases. What is this term? Think about this. What is this summation? From 0 to 1. Amy, your turn again.
Wait, but like, wouldn't that be the same thing?
What's the difference? So here I start at 0. I end at n, right? This one we start at 0, it's the same. To end at 1. What happens if we
Oh.
end at 1?
Okay.
How many terms do we have?
Only one.
0 and 1, only 2.
No. Two. Yeah.
Okay. So this will be Kira, next one. If we end at 2.
Then that would be 3 terms, 0, 1, and 2.
Okay. Yes, Aaron.
Oh, sorry, my thing was unmuted.
Okay. Yeah, I have some comments. So you can see this notation may be a little bit abstract, but it's just short for these long expressions. Okay, now we are ready to
question.
prove. Yes.
For that two summation, the summation with the 2 on top, how come it's yeah, right, that's
Yeah, that's a mistake. Okay, thank you. That's a mistake. Okay. So now we want to check how do we prove this? For all n equals 1. Let's check a few cases. When n equals 1, we have this expression. Either this or less than 2. Okay. It's not less than 1 since we start at 0. Correction, this should be less than 2. Okay, now let's check. Aaron, is this less than 2?
Let's see, 1/1 plus 1/2. Okay. That is less than 2.
Okay, checked.
Because
By
it's
Aaron.
basically 1 plus 1/2, basically.
And Jessica, is this less than 2?
No.
Okay, so this what's the
Wait.
first term?
Wait, no, actually, yes.
Yes, okay, again, yes, checked by Jessica. Yes. So we could check this one by one, but there are infinite many terms. So how do we check this? For infinite many terms, we use mathematical induction. We start with the basic case. In this case, P1. Okay, we verified this by Aaron, so we take that for granted. Then this inductive hypothesis. Okay, put the markup there, check. Let's assume that PK is true. Okay, so this is the hypothesis. Then we're ready for the inductive step. We want to check, is PK plus 1 true? Could we get PK plus 1? Okay. So PK plus 1, let's write down the statement. Is this less than 2? So we want to use this hypothesis. How do we use it in this proof? Okay, Kira. Mhm.
I want to point out, I think in the base case, you wrote the,
Okay,
is this supposed to be
2.
greater than less than 2?
Yes. I keep using 1 because I will start at 0, so it should be 2. Yes, that's correct. You are right. This should be 2. I keep using 1, but that's a mistake. Okay, thank you. So here there are possibilities. We could, okay, there is PK. If we use this directly, let's see what we can get. So the first approach, we recognize then by the hypothesis, the first term is less than 2. Could we conclude this less than 2? Aaron, what do you say?
Yeah. Because no matter how small the fraction you add, you can still get a less than 2 if the fraction depends. But then that, okay, that's, wait. Is that 2 or not?
2, because the hypothesis, this is less than 2. We
Oh,
use the hypothesis here,
what's that thing before the 2?
less than.
Oh, less than 2. Okay.
So I use the hypothesis in this step.
So that's more than 2 or less than 2.
Okay, so now the problem over there, if we use the hypothesis directly, this thing is bigger than 2. we cannot get what we want. This doesn't work.
I was confused. Is that a less than 2 or more than 2?
It's incorrect.
No, the first 2, the first digit. The first 2, not the second one.
I mean this one.
Yeah, this one. Was that more than 2 or less than 2?
That's the hypothesis.
Oh, I see. Okay.
Okay. The hypothesis used there, but it doesn't work. So we will modify this. Instead of the first k terms, we will go with second k terms, the last k terms. Okay. Let's compare this with this. What's the difference and the similarity between them? Jessica, what do you think about this? This one, okay, start at 0, end at k. Start at 1, end at k plus 1. So they have the same number of terms. So, but each of this, the index is bigger than this by 1. So we can see this part is actually half of this. Okay, so that is our observation. Second attempt. I will split the first one as to the 1. So use the formula 2 to the k plus 1. Okay, so verify this formula. Use it for all the terms over there. I get I split this 1 by 1. Now this 1/2 is a common factor for the second part. We pull that out. And this is I can say about it. I don't have to rewrite it. It's just 1. So instead of using the first k plus terms, we use the last k plus 1 terms. We end with the same term, but with a half of in front of it. Now we can apply the inductive hypothesis. This part is less than 2 by our hypothesis. So I put H over there to indicate we used our hypothesis at this step. Maybe I also put H here, indicate we use the hypothesis. Now it's easy. 1/2 times 2 just 1. So this is 1 plus 1 equals 2. Okay. So this completes the proof for the inductive step. We use the hypothesis that this is less than 2 and derived this is also less than 2. This completes the inductive step with also complete the proof of the theorem. Okay, so you can see this is a not a very easy example. How do we prove this? If we apply this hypothesis naively, we get something that is bigger than 2. We cannot get what we want. So we do a little bit of trick over there. We group them together, which give us half of this term in the hypothesis. Then we apply the hypothesis, simplify, we get the upper bound. Yes, Kira.
Doesn't that still like not meet the hypothesis because it's supposed to be less than 2?
What do you mean?
Like the hypothesis was like whatever, like the summation 1, like yeah, it's less than 2. It's not less than or equal to 2. But then you get equal to 2 at the bottom.
Okay, that's a good question. In the end, we have equal to 2, right? But as long as there is one strictly less in any of the steps, then the total will be strictly less. We can have as many as equal signs in between. As long as there's one strictly less, then this will be less than this. Okay, so let me see. So A less than equal to B less than C less than equal to D. Could we conclude A less than D, Kira? Yes, right? Okay, so it's the same thing here. This equal sign, all of them are equal as long as there's one less, it will be less. Because they are all the same. They are all the same. This is the same as this, which is less than this, which is the same as 2. Okay. Okay. Other questions? Aaron, do you have questions?
So you're saying less than 2 plus, well, less than 1 plus 1/2 times 2 equals 1 plus 1.
Uh-huh.
Okay. But that says, but it said less than 2. That the hypothesis thing.
Mm-hmm.
But
Hypothesis is this less than 2.
but it says equals 2.
You mean this is the hypothesis.
Yeah.
Is less than 2,
The result is equals to 2.
which is, I'm not sure. So result here or where?
So
You mean here?
yeah.
Okay. So that's the same thing Kira asked. So this equals to this, equal to this, equal to this is less than 2, right?
So you're saying less than 1 plus 1 is less than 2?
Mm-hmm.
Okay.
No. Okay, so this is less than 2, right?
Okay.
Because this is less than 2, we multiply by 1/2. This is less, add 1, so this is less than this.
So 1 plus less than 1 equals. Oh, I
Okay,
see.
then, so
Wait. Oh.
if A less than 2, now we want to say 1 plus 1/2 A also less than 2. Could you check this, Aaron? Is this true?
Could be.
Could be.
Or there's equal chances that it could be and it couldn't, because this is less than 2. So what if we're like, say, 1.5? Then 1 plus 1.5 wouldn't be greater than 2. But then if it were 0.5, then that'd be 1.5. So there's equal chances, basically.
So whatever number you give me, as long as it's less than 2, then 1/2 of it will be less than 1, right?
Oh, wait, there's 1/2. Never mind. Okay, yeah, that is less than 2.
Okay, so this is definitely less than 2. That's what we had over there. Because this is less than 2, 1/2, add 1, this is also less than 2.
You're saying that the hypothesis is less than 2, and then 1/2 of that is... Oh, I see now.
Yeah, the hypothesis of this is less than 2. The 1/2 of it is less than 1. We add 1, it's still less than 2.
I see.
It's the same thing over there. Okay, very good.
What
Okay.
about geometry?
Okay. So why do we have so many proofs? We haven't introduced geometry yet, because in geometry, some of the proofs are very subtle. We want to make sure you understand the proof, then we give proofs of geometries.
Oh.
Okay. So one
Proofs
more.
related to geometry?
I'm sorry, what's that?
So you're saying that proofs is related to geometry?
There are a lot of proofs in geometry, and sometimes the naive proof is incorrect. So you have to be very careful when you deal with the proofs of a geometric statement.
I see.
There are a lot of conditions to check. So now we have some practice. When I'm ready, we move to geometry. Okay.
Oh.
Okay. So maybe we can skip that one. We can leave that as homework. Let's move to geometry since you want it very badly. Okay. So the starting point of the geometry is this Euclid. Okay, Jessica, have you seen this name before? No? Okay. And Fred, what about you? Euclid. Fred? Okay, so we had a theorem about this Euclid, that there are infinitely many prime numbers. The same Euclid, he is also the one laid the foundation for geometry. So his 5
geometry. What is Euclid?
Euclid.
What? Mm,
Some use axioms. Some also use postulate. They're the same, essentially the same thing. These 5 axioms are the foundation for the Euclid geometry. Okay, what are they? The first 4 of them are straightforward, but the 5th is a little bit tricky and that leads to a lot of discussion. The first postulate, I will use P for short. A straight line. Very simple idea. You give 2 points, you can draw a line going through both of them. So in other words, we can say this unique line passing through any 2 points. Okay, that's the first postulate. Geometry is very easy. 2 points, 1 line. Okay, the second postulate. A straight segment can be extended. Again, it's very easy. We have a segment. Then we can extend this to a line. The third. So you give a point, we call the center of the circle, and a radius. Center, radius. Okay. A circle can be drawn with any center and any radius. Third, fourth. All right angles are equal to another. So here we use equal. Some of you may prefer congruent. Okay, so now it's the term. When do we say congruent? When do we say equal? Two angles.
What is
So
that?
this, which
What is
one?
that?
You mean this one?
The one to the right, obviously. Oh,
Okay, so in some books they emphasize the difference between two angles being equal and two angles being congruent. Can you, Kira, what's the difference between the two?
I don't really know. You could say
Uh-huh.
that equal, like the angle measure is the same, and then congruent, because congruent is like the same in shape. I don't know.
Okay, okay. Okay, that's good attempt. Amy, what do you think? Equal and congruent, what's the difference?
Well, equal is like the you can't really describe, like if you say a circle is equal to another circle, I don't think that makes sense. But if you say like the circle is congruent to that circle, it makes sense. But if you say the circle's radius is equal to that other circle's radius, that would like be valid. So I feel like equal is like for numbers, and then congruent is just for like geometrical.
Okay, yes, very nice. So here, when we say congruent, it's about the relationship between two geometric objects. Also between two different. For example, we have a circle of radius 1. Another circle of radius 1. The two circles, same radius, but in different locations. They are different circles. Because they have the same radius, they are congruent. Circle 1, circle 2. So circle 1 is different, but they have the same radius, congruent. Equal. Okay, two geometric objects, the circles, they have the same area, same length, so circumference. For example, we can see the area of C1 is the same of this area. This area, the length in our case, you have two angles. These two angles, we call this alpha, beta. They are at different locations, they are different angles, but the measurement different angles. If they have the same measurement, if we can rotate or translate this such that the two sides overlap, then they have the same measurement. Okay. But sometimes we still use alpha equal beta. And you will see this in many math books. Why? So sometimes we use alpha and beta also for the measurement. We write this alpha, beta. It depends the context. Do we mean this as the concrete angle, or do we mean it's the measurement? If we mean it's the measurement, we can see the two angles have the same measurement, it's the same. So depend on what's the emphasis of the notation. Okay, so if we want to be very rigorous, we should use this notation for different angles, congruent. But very often I will use this equal sign because we have this measurement in our mind. For example, if I write an angle is a right angle, Draw the graph. I will use alpha is 90 degree. Okay, so here alpha is the angle, but it also stands for the measurement. In this way, we say alpha equals 90 degree. We didn't use, so it's not alpha congruent 90 degree. This doesn't make sense. Aaron, does this answer your question? Congruent and equal?
Yeah.
Okay, kind of. So still there's some sometimes when you say this, do we mean the angle or the measurement? So sometimes there's some ambiguity, but we should be able to figure out. Okay. Okay, so now
Can you go back
the
down? I want to copy some stuff.
okay.
Okay.
Congruent, equal.
Okay.
Okay. So the first four postulates, you can say they're kind of precise and very short. The fifth one is very long and complicated, and there are a lot of discussion about this.
Okay.
Okay. The fifth one, we spend some time. Okay, let's have a 5 minutes break. After the break, we will start with the fifth postulate. We'll be back at 31, 8:31.
All right.
Okay. Okay, so the first four postulates or axioms, they're kind of very easy to understand. And 2 points, there's a unique line. And a segment can be extended to a line. Center, radius, we can draw a unique circle. All right angles equal to each other. Okay. There's no ambiguity. The fifth one involved and lot of ambiguity. Fifth one is also known as the parallel postulate. Okay, a little bit long, and so what it means. So we have two straight lines. Draw two straight lines. Now consider another straight line falls on to down. Now we check the two interior angles. This postulate states that if the summation of these two interior angles on the same side is less than a flat angle, then these two lines will intersect on the same side. This one, if we extend it a little bit, okay, the two lines intersect on the same side. What happens if this bigger than? Okay, question. If it's less than 180 degrees, the two lines intersect on the same side. If it's bigger than this, will the line intersect or they do not intersect? Jessica, what do you see? And Amy, what happens to these two lines if the two interior angles on the same side is bigger than a flat angle?
Then the
Do they still intersect at the same side?
no.
No, okay. What happens?
Uh,
Or they do not intersect at all?
I don't know if it's like, because I know if it's like they add up to 180, then it has to be 90. But if it's greater than 180, is it like even possible?
Okay, so one way to view this is we consider the supplementary angles. Let me draw a different picture. Not the color, emphasize the difference.
Oh, wait, yeah, they would just intersect on the other side, right?
Okay, yes, very nice. Alpha and beta. So alpha plus beta is bigger than 180, then the complement angle. So we call this gamma delta. Okay, not a good notation, but just for this purpose. I claim okay, let's see how do we verify this? Why is this true? Aaron, what do you say?
Because both angles, I mean, both block lines are like faced away from each other until they intersect on the interior side. So like
Mm-hmm.
that's vice versa, then that has to work too.
Okay. So that's a different way to prove it. So here, my way to prove this is because gamma is 180 proof, a direct proof. It's a supplementary angle. The base delta is supplementary angle. Now, so this will be 180 degree, another 180 degree minus alpha plus beta. By our hypothesis, the summation is bigger than 180. So this will be negative. The total will be less than 180. Okay. With this new information at hand, we conclude by the postulate, parallel postulate, they will intersect on this side. The conclusion is they intersect the two lines. By the P5. So, okay, so now let's put them together. If it's less than 180 degree intersect on the same side, it's bigger than this intersect on the other side. The only remaining case is when they are equal. When they are equal, they do not intersect. The only remaining case. In this case, we call them parallel. and we use the notation. And one, if they are parallel. Yes, correct.
I have a question about the previous part, like the proof for this one. So you said that, well, 180 minus alpha plus 180 minus beta, and then it says 180 plus 180 minus that. Shouldn't it be 180 minus?
Okay.
180 minus
Okay,
that?
so let's drop the parentheses, right? We can drop the parentheses because it's addition. Now we have 180, another 180, right? Then we subtract alpha, subtract beta, maybe subtract the summation. Yeah, Kira, what do you think?
Would how would that be smaller than 180?
So our assumption is,
Oh, because it's greater than 180. So
yeah,
basically, 180 plus 180 minus something bigger.
Mm-hmm.
Oh, okay.
So this is the bigger, so this part will be a negative number, so it's less than the first one.
Got it.
Mhm. Okay, cool. Okay. So this is under this condition, this two less than the parallel first angle, it is intersect on this same side of delta. Okay. So because of this fifth postulate is also called parallel postulate.
Question.
Yes, Aaron.
What does transversal mean?
So here called the straight line falling on two straight lines. And then later we will call this a transversal.
Oh.
Okay, so this is our transversal. If we give this name, then just separate the rows for this line and these two lines. This will serve as the transversal.
So it's basically shaped in a triangle in this example.
Well, so that is not the focus of this postulate. So we treat them as just the lines.
Yeah.
Yes, there is a triangle when the two lines intersect.
Yeah, I see that.
Okay.
All right.
Okay, so now we have some very simple theorems. Okay, let's see. We want to build all of our future theorems on these 5 postulates. P1 through P5, foundation. So this Euclid and Euclidean. So it's Euclid's geometry, Euclidean geometry. lot of words, but the picture is very easy. We have two parallel lines. And a transversal. The two interior angles on the same side, alpha, beta. Then we see that alpha plus beta must be 180. That's easy, as we have seen before. If it's less than 180, the two lines will intersect on the same side. If it's bigger than 180, the two lines will intersect on the opposite side. Since they are parallel, we cannot have that. Okay, very straightforward theorem, so I skip the proof. Now some consequences of the theorem. We call it corollaries. Okay. Corollaries, there's some properties can be derived quickly from the theorem. In the same setting,
What's corollary?
corollary.
It
So,
says it looks like corollary.
okay, let me rewrite. Corollary.
Okay.
So this is also a theorem, but the theorem who can be derived easily from a big given theorem. So we call it corollaries, to follow from other ones. Okay, now is a good time to review this notation. What are corresponding angles? Redraw the picture. Redraw the picture. And label this 1, 2, 3, 4. Okay, Amy, what are corresponding angles?
Like 5 and 1 would be a corresponding angle.
Okay, angle 1 and angle 5.
Angle
A pair. Okay, Aaron?
4 and 8.
Okay. There are 4 pairs, so 4 and 8. This corollary states that each of these pair must be congruent. They have the same measure and width. So for this, we will give a direct proof. Because the two lines are parallel, to show that they are congruent, we noted that 1 and 8. Summation of the two should be a flat angle. Similarly, 5 and 8, the summation of this is also a flat angle. Okay, for different reasons. Okay, Jessica, what's the reason for this one? Why the summation is a flat angle?
Because like the entire like angle of of them added is just 180 because
Okay.
the angle of the
Yes.
straight line is 180.
Yes, because they are supplementary angles. And Kira, why the addition of these two is 180?
Because like the fifth postulate said, the interior angles on the same side of parallel lines will equal 180.
Okay, yes, so that's the previous theorem. It must be 180. Now the two angles, 1 and 5, they both supplement to angle 8. This implies this is why the corresponding angles are the same. Okay, very quick proof. What are the alternating angles?
The what?
Alternate.
Oh, alternate. Oh, 4 and 7.
4 and 7.
I mean, no, 4 and 6, 4 and 6, 4 and 6.
4 and 6. Okay, to make it easier for drawing, I will go this 1 and 7. It's the same thing.
Yeah.
Now we claim they are also the same. Could you give me a quick proof why they are the same? It's a similar. Okay, Kira, what do you see? How do you check these two angles?
Since the lines are parallel and they're crossed by the same transversal, then I guess the angles on like the interior on opposite sides would be equal because the parallel lines cross like the transversal at the same degree.
Okay, so now that is correct, but we want to build our proof only on the postulates, the 5 postulates. So now we use similar stuff. 1 and 8 supplementary, 7 and 8 supplementary. So 1 and 7 supplementary to the same angle. Therefore, 1 and 7 must be the same. Okay, so I will ask you to finish this proof. Finish this proof. Okay, so I will stop here and I will check any questions.